Hello. So today we have a video tutorial about Ansys. Ansys 19 actually. I'm now in Space Plane and I've modeled this structure here, which is an IPE 330 with welded to square hollow section. The welding has 2 centimeters. And our purpose today is to perform a static analysis in this welding. So, in order to perform the analysis, we have to import the geometry to mechanical, and then perform every define properly every property that the mechanical requires. So the first thing that we have to consider is the material. I've applied a nonlinear steel to the welding and to the IPE, and the linear material to the whole section, because it's not what I want to analyze today. What is the most important thing is this region here. That's what I want to perform. That's what I want to analyze. So, after defining properly the material, I can show you that I have structural steel nonlinear for the IPE. For the whole section, I have a structural steel, a default structural steel, and for the welding, I have a structural steel nonlinear too. So, after defining properly the geometry, we have to perform a contact definition. So between the whole section and the IPE, I've defined that it has a frictionless contact, because I want to make sure that what is properly connecting the whole section to the IPE is not a bonded contact between these two bodies, but the welding. So in order to do that, I perform the bonded contact between the welding, the welding and the IPE, and also a bonded contact between the welding and the hollow section. Every contact is set as it should be. I can perform an initial contact results here now. And we will see that every contact is properly defined. Yes, as you can see, no warnings. So, after defining the contacts, I've performed the mesh attribution. I've set the parameters to the mesh. It's not perfect, but it works. That's what I want to do today. It works. So after defining the mesh, and keep in mind that we have to have a good mesh to perform a nonlinear analysis, otherwise we won't have good results. So I've defined then the analysis parameters. I've established 2 steps, one to apply the force and the other one to take out that force. I've applied the force of 52 kilonewtons in that direction. Okay, I can show you that direction. Okay, so we will see how the beam and the whole section and the welding behaves in order to make a flexing in this part of the structure and of the connection. I've established a fixed support. This is very important, otherwise we can get errors like rigid body motion. So this part of the beam, the end part of the beam of the IPE is established as a fixed support, and we don't have any other fixed support or any other restrictions, just a remote force and a fixed support. We are now we have conditions to run the analysis, and the first thing that I've noticed, so this is the solution now. The first thing that I've noticed is that we have 144 millimeters of displacement. In the total displacement, of course, this displacement is mainly in the x direction. We can perform a detailed analysis in the x direction. In the equivalent stress, this is the total equivalent stress, okay? So we can see that it reaches 7,000 megapascal, which is absolutely abnormal. Okay, this is not true, and the maximum stress, of course, that is in the structural steel, since it is a linear structural steel. But what is important in this analysis is not the stress in this in the whole section, but yes, in the welding. So I've performed a detailed analysis in the only in the welding and in the IPE, and as you can see, we reach 730 megapascal, 730 megapascal. The material that we used is the structural steel nonlinear, and it has a yield strength of 250 megapascal. So we can see clearly that the steel enters in the plastic zone, maybe even gets to the failure. And of course, that the biggest stress is in the tension zone. Yes, it's in this part here. And of course that in the compressive zone we have lower stresses. This is in true scale, so this is to be what happens in reality when we have this material. And in my opinion, it's very good, the analysis. We have a clearly nonlinear analysis. And this is at the end of the first step, of course, but we can go to the end of the second step, yes, which is when we take off the force and we have lower tensions. And you can see it by the graph here. So this is the deformation at the end of the analysis, and at the end of the analysis we have a deformation of 144, so it's not very far from the 178 that we have in the beginning. Also, we have I've set a lot of points to define the stress and to analyze the stress in that point. And I hope that you've liked this tutorial. This is a quick tutorial just to show you a basic nonlinear analysis in a T-connection, in a T-joint. So hopefully, I think that I've showed you what really matters in this analysis, and hopefully you will learn something from this. Thank you for your attention.